Here we are at part 2 of section 6.2. I saved this for a separate video. We're going to rationalize the denominator. It sounds scarier than it really is. They start off with something simple with example 5. Rationalize the denominator means make the denominator a number. Make it a whole number. It can't have a radical in it. So we need to get rid of the radical. In something like this, it's easy because we view this as square root of 3 over square root of 4. We know the square root of 4 is just 2. So square root of 3 over 2. That's how I rationalize the denominator when it's a simple one. Now, here they give us a number that isn't a perfect square. We can still view it this way, but the idea is how do we get 6? Well, when we have the square root of any number, if we want to get just the number, then we multiply by the square root. Multiplying by the square root, well, we'll do it right here. We'll say, let's say we have square root of 6, and we multiply by the square root of 6. I'll go like this. When we do that, we're essentially saying the square root of 6 times 6, square root of 36, equals 6. If you follow along with that thinking, that thought process, that's what we're going to do every time. We need to get this number, or a number. We need to get a number on the bottom. When we have a square root, all we do is multiply by itself. Square root of 6, we multiply by square root of 6. The square root will fall away because essentially we're multiplying that number by itself underneath to get the square root. That's why it goes away. Now, whatever we do down here, we have to do on the top. So I multiply square root of 6 by square root of 6 to get my 6. I have to multiply square root of 5 times the square root of 6. And I'll do it like this so everything follows along. Square root of 30. In this case, we could break that down and say that's the square root of 3 times 10. It's the square root of 2 times 15. What we're doing is we are looking for any perfect squares we can get. We could go up to 5 times 6. Either way, when we look at this, I can't draw anything out. So I leave it, my factors we have 2, 3, 5, 6, 10, 15. No matter how we break it down, we don't have a perfect square that we can draw out. So we leave it square root of 30 over 6. Then, now had we been able to pull something out, if we had square root of 32, we'd have 16 times 2 and we'd draw out a 4. But we're going to leave it like that for the answer. Now example 9 is where they try to throw us off a bit. They give us a cubed root of 4. And when they give us something like this, there's a lot of thought involved in this. We need to think of a perfect cube that 4 divides into, and how do we get that? You know by now that 8 has a perfect cube root. Cube root of 8 is 2. I know that 4 goes into 8. So what I need to do is I need to get an 8. I need over here, I need a cube root of 8. Because if I get a cube root of 8, I have 2 and I have rationalized the denominator. So I need to multiply. Let me try a different color here and see if it'll work. I need to multiply by a cube root of something that will give me 8. If I multiply by the cube root of 2, cube root of 4 times cube root of 2, as long as our index is the same, we can multiply the numbers together underneath. So we need the missing component that will lead to a perfect cube. That's the thought process here. I remember when I first used to do these, when I first learned how to do them, I had this mentality throughout. So I would try multiplying cube root of 4 by cube root of 4 and getting 4. Then I realized that doesn't work. So cube root of 4 times cube root of 2, that gives me a cube root of 8. So up here I multiply by the cube root of 2. And I end up with 7 times the cube root of 2 over cube root of 8, which is 7 cube root of 2 over 2. That's my answer. It's a little tricky, and apparently the charger did not charge my battery because I'm dying. We only have one more to do. We'll do example 10. Hopefully we get through example 10. We use the same thought process that we just used for example 10, where they give us square root of, and then they give us a whole bunch of different items. 12x to the 5th y cubed over 5z. Regardless, we think of this as 12x to the 5th y cubed all over square root of 5z. Now again, we already discussed the idea that we can multiply by 5z to get that square root to go away. Doesn't matter what it is. If we multiply a square root by a square root, whatever we had underneath is what we're left with. So up here, I have square root times square root, so I combine all this, and I had a 12, and I'm multiplying by a 5. I had an x5, y3, and a z. And that's all over 5z. So now I simply look at this and say, is there a perfect square that I can pull out of here? And what I have is the square root of 4 times 3 times 5. I do have a perfect square right here that I can pull out. And then I have times x to the 5th. I can say that's times x to the 4th, x1. And y cubed, I can pull a square out of there. And then times z. So I'm going to work with the numerator now. Square root of 4 is 2. Square root of x to the 4th is x squared. Square root of y squared is y. And I am left with square root of 15 x, y, z. That z is under the square root symbol. That's all over 5z. I think that was the last example I wanted to do for this particular section. I'm breaking it down. This was just rationalizing the denominator. And then we're going to move to square root of a perfect square for the final video for section 6.2. See you in a little bit.